back to, let's say, a university, and soon helped to initiate the setup of the Amstel Institute, Center for Science Education. After the discontinuation of the Amstel Institute, I went back to the first love, mathematics and the Mathematics Institute, but I kept going doing educational research instead of mathematics research. And I finished my doctoral thesis on mathematics and science education. And currently, or the last couple of years, I work a lot on the curriculum design and lecturing mathematics for life science students and computer science students. And I promised I will also talk about examples of inquiry-based mathematics education tryouts in this area. So I will talk about a developmental project which has been taking place in the last 3 years at let's say 7 countries, 8 universities in the Erasmus Plus program. So please, the next slide. This will. I guess that Rogier, are you controlling? Then
yes,
maybe yes. Sometimes you think, well, I'll just press the button because then items will pop up and I don't have to ask continuously.
Yeah, I'll try to do it. Yeah.
So Platinum is actually an acronym. It stands for Partnership for Learning and Teaching in University Mathematics. If you have a project, you first think about the acronym. And it has applied for an Erasmus project on inquiry-based mathematics education at university level. And the partners are the University of Agder, who did the project coordination and was supported by the Matric Center. Then I have listed in red the 3 universities where mathematics educators or educational researchers were involved. That's the group of Barbara Jaworski in the Loughborough University, the group of Heinrich Hochmuth from Leibniz University in Hanover, and the third group is from Ines Gomez-Chacon from the Complutense University. And down in the list are in blue, the universities where no educational researchers were involved, just lecturers in mathematics. 2 universities in Brno, the Masaryk University and the University of Technology, and the Boris Grynchenko Kiev University in Ukraine. And I've placed the University of Amsterdam in the middle because, well, we are lecturing mathematicians, but also at least 2 of the people involved had experience in educational research. And of course, there are external partners and organizations. So Rogier, continue. The short statement about what were the ambitions of the Platinum team and in terms of mathematics education. And what we wanted is like what many teachers want is to improve their teaching. But we had a clear intention to shift the balance between, or the misbalance between rote learning and procedural understanding of mathematics and conceptual understanding of mathematics, that we wanted to shift the balance more towards conceptual understanding. And also with the goal that we think that in this way students are, say, better prepared for their university studies and also for the workplace. Yes, no, that's fine. If you go too early up, that's not a problem. And it says that we wanted to try out inquiry approaches in our teaching, and also in this way find out what kind of inquiry is manageable, doable, and can we figure out to do or like to do. And the idea is, of course, that we want to improve the students' understanding of mathematics, to engage them more with the mathematics, and also to let them enjoy more the mathematics. And if you want them to do inquiry, it's all about what kind of tasks are you going to give to them, and maybe also the exams. But let's first think about tasks. You design tasks for them, and we try them out in regular courses. It's not like an experiment that you want to do, but it's really intended from the start that we are going to use them in the regular mathematics courses. And not only use them, but also to evaluate and to look about how it worked, but also look a bit critical to our own teaching. And you don't do this only as one person on yourself, but you form what we will call the community of inquiry. So you do it together with colleagues, and that's done in local communities, but also in the communities at different partner institutes coming together and discussing inquiry-based mathematics education and their experiences. And of course, we want to disseminate the project results, and that we did this also by designing and conducting workshops for colleagues during the project. It was mostly done in the first year, but also in teacher training, etc. And the major outcome, I could almost say, is that we have managed to produce a book about the project, the case studies done at the partner institutes, and yeah, Paul shows it. It's a real book. For those who have not received one, I think I still have 4 copies left. But it's also available as an ebook, open access, and it's published by Maastricht University Press. So at the start, we were, of course, first thinking about what does engagement with mathematics for mathematics learning through inquiry, what does that mean for students? And that has to do with what I said, the shift from rote learning, focusing on methods and techniques, more toward memorizing facts, to another approach that we would focus more with students on concepts, and that they would inquire into the mathematics. And this engagement of students, we want to be also purposefully. So it's many times connected with in what kind of course are they, in what kind of discipline they are studying, and to engage in a positive way. Yeah? As I said, it is also meant to be a kind of stimulus to study mathematics, that it's good to study mathematics, even in studies where you may not expect it so much, and to have a positive experience of doing mathematics. And the positive experience, I think, in our eyes was also that you more inquire into the mathematical concepts and mathematical relationships, and that the focus is on the why questions. Why would you do this? Could it be done in a different way? And so students, they explore possibilities to do things differently, to look for alternatives, look at solutions. Maybe there are many solutions possible, and you try to evaluate your answers. And also, it's not like doing exercises on your own, but students are expected to talk more about the mathematics with their peers. It's in the group work that you organize, and that they, in this way, explore more together. And I think that's yes. Now, what does it mean for the lecturers, actually, this inquiry work? And having students in your classrooms, in your lecture rooms, being involved in the inquiry. Well, at first, of course, you have to encourage them to engage really in the kind of task that you offer them. And this is done by asking more open questions, but also by encouraging students to ask their own questions in the lessons. And well, it's means for lecturers that you want to create opportunities for student collaboration in inquiry activities. We will see examples of this, what we made. And it's also an inquiry for us personal as a lecturer, because you inquire in your own style of teaching and your own way of engaging with students, and you reflect on your own business, actually, the things that you do. And well, we set out to try new approaches for our own teaching, to evaluate them, to look critically at the outcomes. And we consider here, actually, in that sense, it was kind of experiments. If it was not as we expected, or outcomes were not so positive, we would consider that not as a kind of, well, retreat, but a stimulus to go on, to try something new, to try to understand what went wrong. And of course, as lecturers, we don't do this on our own, but we collaborate with colleagues to innovate and to explore. You cannot do that all by yourself. That increases your workload far too much. So there are two concepts I want to discuss, which were important for the setting of the Platinum project and the way we worked, and that is the concept of community of inquiry introduced by Barbara Jaworski. And in this case, it is, of course, linked to communities of practice of Etienne Wenger, but we try to look at it from a very simple perspective, like, okay, there must be at least a group of two, and it's a community of inquiry, so they do inquiry. And they learn through inquiry. So you really want to know something, want to change something, and you want to find out if what you thought that would be a good approach or a good solution to something. You seek to find out if it works and if it can be improved. A community must have shared purposes. You must at least agree a bit upon what you think that IBME means, inquiry-based mathematics education means for you, and how you want to work together, what goals you want to fulfill. And in a community that works better, because you can talk, of course, to yourself about this kind of, well, what are my goals? But when you talk about it, it's like with the students in the class, when you talk about it, then you get better ideas. And that's what is actually in this last point said. Well, it helps that you can have colleagues to discuss with. And well, it's all about actions, learning, and knowing in this community. And so if you press some buttons, then you can see that there's sharing of the design of teaching, reflecting on the learning outcomes. That are the kind of things you do in a community of inquiry. You relate to what others have written. It's a kind of research. You look what is done in the literature, what your colleagues are doing. You try to gain insight in ideas and possibilities, and try to find out, to try out new ways of working with the students. Now that builds up your knowledge, you learn, so to speak, and in this learning process, you gain some knowledge of how to use, how IBME works for you in practice, and then you have a kind of cycle that you reflect on how it went in the classroom, and you increase your learning. Okay, you can move to the next slide. So we have a community of inquiry, and this inquiry happens at 3 layers. Barbara Jaworski has also discussed much about a 3-layer model of inquiry. You have inquiry that takes place in the classroom, in our case at university settings in lectures, tutorials, workshops. There is an inquiry of the lectures or between the lectures, when they explore about mathematics teaching. They think about, well, how could we design some tasks? How could we use them with our students? And then you have the exploration, the inquiry of the lecturers together maybe with mathematics educators on collecting data and analyzing what happened in the classroom. And so you develop knowledge about your practice. And this can be visualized in a layer model with core layer, which is about the inquiry and mathematics done by students or with students, because teachers are engaged there as well in the classroom, in the lectures, in the tutorials, in the workshops. Then you have the lecturers who explore the learning of mathematics teaching. And finally, we have collection of data, and you analyze these data to feedback to inform practice. Now, I think the next slide is about filling it in with what kind of tasks are done. Yeah, you can go to the, yeah, so here you see the inquiry that the community of inquiry does is happening at all the three layers. So you can have lecturers designing tasks, then they are in the middle layer. They can use these tasks in sessions with students. The students engage with the inquiry, then you are in the course of the model. We have lectures reflecting on what happens in the classroom, what are the outcomes, and refines the task. Then you are again in the middle layer. The students developing understanding, that's in the core, and collection of data and analysis of outcomes, that's more with the developmental research inquiry connected. I think that was it. Yeah, no. Yeah, well, research or inquiry you share with others, because you could say, well, it's only research when you publish about it, but for us it's more like that you discuss with others what have been learned, and that it was in the partnership important that you discuss what is happening at the various local communities of inquiry. And in the first year we had 3 two-day workshops about that, where we could at least in the initial stages share our ideas and experiences. And the last 2 years, it was more in the Zoom meetings and the Teams meetings. Okay, let's see what comes next. Oh yeah, an example, because inquiry, well, I still don't know what is the definition also of inquiry-based mathematics education, but it helps if you just look what the different partners create. And in this first example, coming from a course where I will talk a bit later more on, is about computing a numerical derivative. And the background of this task is it is a task which is developed in a basic mathematics course for first-year students in biomedical sciences. In course it's happening in November, December. And actually in the Platinum project, when we started, this course didn't exist. So we had a chance to start from nothing. So to start fresh. And that is interesting because we were the only ones in the project who could develop a whole course with the idea of, well, let's introduce inquiry-based mathematics education elements. So it's part of a basic mathematics course. This course is about it's an introduction to systems dynamics. You can press, so it fits with that. And systems biology, well, you may not be very used to it, but it's actually the area where you study processes of change in a biomedical context or in a life science context. And for mathematicians, that means you're just studying dynamical systems, differential equations. Now, you would say, what has this to do with numerical computing a numerical derivative? Actually, can you go back to the previous slide? You study in life science, of course, growth models. And you look at exponential growth, logistic growth, restricted exponential growth, etc. Now, if you look at the model of exponential growth, and you collect data about this process, then in the standard textbook says, well, you have to transform this exponential function, the solution, to a logarithmic scale, because then you can have a linear fit of your data. But this is actually that you already know the model, but that's very rare. Most of the time, you might want to think of what could be the differential equation, what could be my model. And for that purpose, you could also say, well, if I have my data collected, if I have a way of computing the numerical derivative of my quantity at the points where I've measured, then I can plot this numerical derivative against the quantity, and then I can figure out what kind of models could work well. Because in this particular example of exponential growth, you would see that your numerical derivative plotted against the quantity should be or is with points lying on a straight line through the origin. But of course, if it is not a straight line, but you see, well, it looks like they lie on a parabola, then it might be that you're just with a logistic model more suitable. Now, so computing a numerical derivative is something which is important in this field of systems biology, if you look at from this point of view. And I think then you can move to the next slide. The background continues. So we want that students to, well, it's an inquiry because it's new for students. They are used to getting functions with defined by formula rules and then to compute derivatives. But what to do if you just have data? Then you're talking more or thinking more about the derivative as a real concept, mathematical concept of function. And of course, when you think that you can have students work with numerical derivatives, you must have a feeling that they are able to come up with ideas for numerical derivative. And this is connected strongly with difference quotients at the beginning. Now, it's not a part of the secondary school curriculum, but I think it's still treated by many teachers. But also we did it beforehand already in the course. But what is new is actually that we don't present methods for numerical differentiation, but we invite students to come up with their own methods for doing this. And then I think we get the task that invites them. Oh yes, this is about, well, you as a teacher, you also are very happy when you can imagine what happens before you try it out in classroom, that you can imagine what kind of solutions students could come up with, what kind of methods they could come up with and how you would react to that. So you can anticipate a bit beforehand. Now this activity is used in a lecture. It is not restricted to use in a lecture, but we did it at the last 25 minutes of a 2-hour lecture. And then the students were implementing in the programming language are their own ideas in a tutorial, which was after the lecture the next day. Yes, here's the task. It's a very simple task in terms of, well, not too wordy. You just get a table of data. And the question is, well, you have to figure out if you can, on the basis of these data, find the derivative of y in the middle point, t is 1. And we ask for a best approximation because you want the students to evaluate a bit their methods that they come up with. And up front, we tell them, well, the data were just created with the function e to the power t minus 1. And that has a derivative in 1 equal to 1. So if you have methods, you're in good shape when you get near this best answer. But we give them the task actually to come up with several ideas for doing it. And in the lecture, I said, well, you have to find at least 2. And then you do this with your neighbors, with more students, and you compute your value, and then you compare your methods a bit. Now, it would not be much inquiry if there were not so many solutions, many possibilities. If there are only 1 or 2 things to do, then it's not really interesting. But here, even if you would say, well, it's forward finite difference, if you know what that means, then you can still have a look at what happens with time steps. You can have backward finite differences. You can average a forward and a backward finite difference. And well, you can have weighted sums of forward and backward differences. You can move to Savitsky-Golay formulas, means that you approximate the function by using a small number of data points around the point of interest. Or you could even, in this case, with 5 data points, say, well, have a polynomial fit with degree 4. Now, I've also listed here what are the kind of answers, and you see that there is difference between them. So there is a way of looking at what is the quality of your method. Yes, and then I think it is about experiences. Yes, so when you do this, no, this I already told. In the computer implementation, they could investigate more things like effect of noise, size of the time step. But the experiences. Now, if you try this out in your lecture, at least I think we have done it now 3 times, 25% of your students disengage immediately. They go to their smartphone. Well, there can be reasons for it. They want to get the bus in time, or they leave a breakout room and they just disengage. The engaged students actually, so the other 75%, they propose expectable answers. But certainly the forward and the backward difference method, but also to take the mean of this. And this engagement is also possible after when students already have 7 hours of lectures and tutorials on the day. The first time in 2018, we happened to have our students from 3 to 5, and they had already a busy day with a lecture and 2 tutorial sessions. But even then, they were in this last 25 minutes, so let's say around 4 o'clock in the afternoon, still able to think and to explore. And the reason is that they were at least intrigued by the question. Maybe because it puzzled them that they didn't have a function description, but had to use just points for a numerical derivative. But anyway, it is possible. So that's a kind of success. Well, what doesn't promote success is actually that if you do this in a lecture room, that's not really convenient for student inquiry, because the number of students is large. There are 150 students. Well, they are not luckily all present in the classroom, but maybe 50, 60, 70 are still there. So I've given you already now some impression of what our intentions were and what kind of inquiry that we try. So now I will focus on the third intellectual output, it's called in this Erasmus Plus terminology, what kind of deliverable, and that's the design of inquiry-based tasks. Because that allows me to show what several partners have done and what the experiences were with their materials. So first, let's have a quick look at what we promised. Well, we promised to create tasks, and a group of tasks could be a teaching unit. But these tasks would have to do something with inquiry-based approaches. So to promote conceptual learning through an inquiry approach, that is the main goal that we had. And we also promised that we would blend a wide range of digital and other resources for use in these tasks or by lectures. We would teach them in specific regular courses, collect data about their use and evaluate how it went. And in this way, could create a kind of documentation around the use, around the design task and the use of them in practice, so that they can be used by others in and beyond the project. Then there was in the call, we had promised that we also would spend more time and energy on exploring possibilities to make units accessible for students with special needs. It's an old term, it's now identified needs is more common. You think of visual and hearing impairment or dyslexia, but also in the autism spectrum or in mental health, ADHD. What we could do there. And for that, we adopted the framework of universal design, especially the universal design for learning. And you may have noticed when you read the mathematics teacher journal of the NTCM that universal design of learning is popping up now more often. And we would look at accessibility of digital content. And the idea is, of course, that in this way, we have more inclusive teaching and learning, but you take more into account the diversity of students. And in our case, that also means taking into account that you have a group of students with a mixed mathematics background. In the Netherlands, we have students with mathematics A and mathematics B. And now, for example, you might think that in biomedical sciences, you have to have a profile with mathematics B, but that's not necessary. And that means that about 1/3 of your students has mathematics A as background. So that way you also take your diversity of students into account when you design your tasks. And the idea, of course, of universal design is that you try to help all students. And the bottom line is, if you have something which is good for students with identified needs, that's probably also good for all your students. And we'll see examples of that. And then, of course, we have promised to present our case studies to a wider international audience. And the book is the ultimate thing that we have produced. Yeah. Well, this is just a summary of how the community of inquiries work. They cyclically design student inquiry activities, tasks, and use them in their lessons, evaluate and reflect it. I think this is what I more or less already told in what community of inquiry normally do. And well, there is a repository of documented teaching units, but it is not completely filled yet. We are a bit behind in our deliveries, although the project officially I think is already passed and finished in January. So let's now have look at some of the tasks that were designed and more about what kind of task and how they were developed and how the experience with them were in the classroom. And one of the techniques that we have used a lot in our courses, and when I say our, that's maybe all the Platinum partners, is that we just changed existing questions, making an exercise a little bit more inquiry oriented. And here you see a task which is for students, mathematics students, first year mathematics students. And the task in the textbook I think it came from was about proving that if you have a conversion series of non-negative numbers, that if you raise the terms to a certain power, an exponent greater than 1, then it still converges. But that turned out that it was a too difficult task for the students. And so here you see also what is manageable for, let's say, normal lecturers, regular lecturers, is you don't ask them to document a lot their work, but a short documentation about what was the problem with this exercise, what did I intend to do, and what have I done now, and then just write down, this is my new task. That helps, and that's not too much a burden. And so here you can see that they first, let's look at the particular case, but then at the same time, the inquiry has been broadened by not just saying, well, concentrate on p greater than 1, but do it for a larger range of p-values for this exponent. So there's where the inquiry increases, because then the students have to make differences between what happens with certain p-values. So let's look at another example. This is just more about changing the existing questions. Here's an example. I want to show examples from different partners. This is from Loughborough University. They have a foundation year for students who enter university with a different background. And in this foundation year, they also discuss complex numbers. And they have a tutorial session with 6 tasks about arithmetic of complex numbers. And they want students to make the link between the arithmetic and geometry in the complex plane. And here you see question 4 of the set of 6. They use a dynamic environment for making these connections, and that's Autograph in the UK. That's a popular tool. And in boldface, I have indicated what are the questions which are really more focusing on let students do inquiry. So it says notice what is happening, and that's like the heuristic of John Mason, who formulates it as you can start a mathematics discussion by asking people, just say what you see when you do something. And also you see here the words like explore. So you have to do something. It's your own initiative what you want to explore. We don't tell you exactly what to do. Now, let's look at the next slide. The experiences. Well, although the task may be nicely designed, the problem was that many students did not manage to complete all the tasks in 50 minutes, whereas the lecturers thought, well, that's not a problem. Some of them don't even see these relationships that you are expecting them to see. Students found instructions sometimes too long or too wordy. Yep. And well, there is a certain culture. Is this going to be examined? If not, then maybe I'm not so interested anymore that you are also confronted with. So the challenge for the people in Loughborough was also to adapt the tasks so that all students learn and that they also have more an understanding of that it is worthwhile to know the mathematics more deeply and more conceptually. And I will discuss this length of instructions in the next slides, because that is an example of how you can use universal design principles to improve your tasks also. So this is, I think, a task as it was in one of the first versions. And well, you don't have to read it, but you see there's a lot to read. There are a lot of words. And if you go to the next slides, you could read them more, but it's a lot of words. So the students were actually right that, yeah, this is, but also if you look at the questions, they are very much on right click, do this, calculate by hand, very direct instruction. So now you can shorten it and also make it change the questions, like describe what you see. And does what you think in part D still hold? So this is shorter, more manageable. Then in the next slide, you see that shortening helps, of course, in time management, but maybe not too much, because the time management may have to do that students do not know how much time is expected to be used for the task. And it helps just to add expected times, so that students, if they spend much more time, they might contact others or the teacher to talk about this. So this is already an improvement also for students who have difficulty in the autism spectrum, that the special needs. It helps them to give them indicators so much time, but also for making the connections, well, use of colors. And of course, the colors here of the letters Z should be matching with the colors in your application. That also helps students to explore the situation. So that's why you say universal design or multimedia principles for design, they are useful. And it's more that you have to pay attention to them as a designer. Next example. Well, there are, I see at least one teacher educator, Derek, here. So Loughborough University, no, not Loughborough, in Hanover, Leibniz University in Hanover, they were much involved in pre-service teacher education. And they had designed the following task in Platinum. So they start with a fictional scenario of students sitting in the classroom in high school, and the topic is apparently inflection point, and one student draws the graph 1 and says, well, does it have inflection points on the straight line? And then the other, his neighbor or her neighbor says, no, what to do with the parabola here? If you flatten the bottom like this, do you have a lot of extrema and minima? Infinitely. So the next slide. So the questions raised in this scenario by these students actually is how many inflection points does graph 1 have and how many extrema does graph 2 have? Now, the task for the students in the pre-service mathematics education is first to think about the mathematics of inflection points and find a mathematical answer to these questions, and also to give argumentation for their answer. They do this by writing an essay, by the way. And also to think about when you use this in a classroom setting at secondary school. How would you, what kind of responses do you expect, and how would you react to that? And what didactical goals would you pursue in a discussion of these two questions? Now, it is already shown that, well, we might think that is a nice task for pre-service teachers, but some of the students are very negative about it. They undermine the didactic contract. They say, well, this scenario, students must have made a mistake and it's not a real scenario. Or criticism like it's a waste of my time because in real schools, I will never see this or encounter this kind of pupils or this kind of problem. So you may have good intentions of letting students explore mathematical situations in the profession that they are aiming at, but still it may not fit with the initial, with the culture in the classroom or with all the students' reactions. And then I end with, look at the time. Oh yes, we can still do that. With more have a closer look at the basic mathematics course for biomedical students. So we had our community of inquiry organized around this course. And so 2 lecturers and 4 student lecturers and 1 critical friends were involved in the design and the delivery of this course. And as a core, you have to have a shared goal. And we formulate this as that we wanted to improve the mathematical component of students' biomedical scientific literacy through developing teaching of dynamical systems in the context of biological process. So we select our content because this is was a new course, and I've worked for life sciences for a longer time already. So the program directors have trust. They just say, well, we should have basic mathematics in biomedical sciences. Oh yeah, and at least discuss 3 growth models: exponential growth, limited exponential growth, and logistic growth. But for the rest, do what you think is best. So that's an advantage. And you make benefit of this. So I could decide, okay, there is a track of systems biology in this program, in this bachelor program, and I will make the start of this. And so there are 150 students. They have differing mathematics background, as I said before, mathematics A and B. It's well, it has changed, but the last 2 years, it is an 8 weeks course in November, December with 2-hour lecture and 2-hour tutorials. And as a COI, we collect data about our students, personal data about their math anxiety, test anxiety, motivation, engagement. We used questionnaires for that have been used in the literature. We evaluated the module. We had classroom observations. Also, our critical friend was observing. And in the design phase, we had weekly meetings because don't think that any course is developed well in advance. We are sometimes happy if we have the lecture materials ready 1 or 2 days before the lesson actually happens. So we had weekly meetings where we did note-taking and voice recorded our meetings so that we could use them for inquiry purposes later on, and also for writing our chapters in the Platinum textbook. So the contents is an introduction to systems biology and systems medicine, because the students in biomedical sciences study lots of process of change in biology, but also in the context of the human body, models of health and illness. And we were heading as a COI to quantitative mathematical modeling using ICT. Because the bottom idea was, if I want to study differential equations, and I don't want to disadvantage students of mathematics A who didn't learn about integration, so I have to move to an organization where I can let students study, explore dynamical systems in using ICT without first learning many exact methods. And the idea is that they explore various models to come to grips with biomedical phenomena. It's a mathematics course, but strongly connected with biomedical sciences. And so we let them interpret real data coming from real journal papers. And so this is also the first time that students, the first year students, probably get to read, well, not to read, but to look for the data in a scientific research paper. And our IBME character is rooted in the vision that we want our students to work in ways similar to how mathematicians and scientists work in a biomedical context. This is more from the inquiry-based science education, where it is more common that you let the inquiry be modeled by how physicists work in their profession, or chemists. So what kind of IBME elements, besides this numerical derivative where you have students inventing their own methods, is that we, in the lectures and in working with problem tasks, allow them more to express own ideas. We stimulated that they learn together in small groups. This is also because of the lecture room settings, where if you are with 40 in a small tutorial room, well, there's no walking around or forming groups. It's your neighbors, your immediate neighbors you can talk to. And we created, for example, worksheets that could be used also in the lectures. For example, to study or direction fields of differential equations, to let them sketch solution curves before we treat these concepts in more detail. And then there's a lot of use of ICT. We'll see examples of GeoGebra-based tools that we designed for using during the lectures and tutorials. Also JavaScript-based simulations where GeoGebra didn't work well enough. And it's most of them are for increasing opportunities to have visual explorations. And that was a kind of preparatory work to go to the use of R and R Studio. the students have to learn a lot of to work with R and RStudio, also in the statistics courses. So that's where we linked up with basic statistics. But also later in their studies and as practitioners in life sciences, they use this kind of environments for inquiry work as well. Now here you see an example of, well, this is what the student work. It's a screenshot during an MS Teams session in the COVID period. We were affected by that. I was surprised. I thought that inquiry-based mathematics education would become very difficult in online teaching. Now, it certainly has not made it easier, but it also offered more opportunities. For example, my experience is that helping students with computer programming or using programs in general, it's very convenient that you can share the screen or actually can get control over the screen and help students in this way. In this session, this is a screenshot of a small session of students from double bachelor. You see at least one student with still a happy face. He's smiling, so the joy of mathematics is still present. But that was also because they could help each other. And being a small group of double bachelor students within this 150 students helped them because they knew each other more. And this was actually about working with pharmacokinetic data and writing a script. And now you see already the data points after plotting the derivative against time. That seems to be like a linear fit possible. Next slide, please. What did we intend to do to promote student thinking and reflection doing this in task? Well, as I said before, we rephrased and extended existing questions, but also by asking more about meanings. What does this mean? Can you explain the result that you have? Could it be done in a different way? Are there more answers good for the or possible? We pay much more attention to the mathematical methods, on what actually underpins the mathematical methods, and the representations that are used. We pay much more attention to, certainly in this field of differential equations, where there is a lot of representation going on. We let students give argumentations for their answers. And certainly when they explore alternative methods and techniques. Yep. Go here, you can press.
Yes, just we usually leave a bit of time for discussion in the
yes,
end.
Well, we are quite to the end.
All right, great.
No, I know that. And so as a COI, we looked, of course, when we knew that differential equations and inquiry-based methods would be our goal. We looked at what is written about it in the literature. There is a nice review on classroom methodologies for teaching and learning ordinary differential equations in 2021. That came at the end of our project, but we had a very close look at the IOD project of Chris Rasmussen and others, where they have implemented what they call inquiry-oriented mathematics education and an RME-based approach. And in the end, we decided we will not go in that direction. And that was mostly for pragmatic reasons, too short course time, rooms unfit. We have no way of inquiring really into the student thinking, but also that there was a mismatch anticipated with the RME principles, like the guided reinvention principle, emergent modeling, making use of students' own inscriptions, and the dominant teaching culture in the life sciences. You're not the only course that the students take. And if the dominant teaching culture differs so much from what you would do if you take an RME approach, that would give a problem. That's why we decided we'll not do that. Although there are nice examples of students letting in invent and learn about bifurcations in the experiments done by Chris Rasmussen and Simon Goodchild in Agder. But we didn't have the time. Then there are universal design principles. Well, it's the main principle is the less is more principle for the design. We use the sowieso environment, let's say the numbers for higher education. We have randomized exercises, and that can be also GeoGebra-based exercise to make a kind of small environment where students can do a particular task, like drawing a linear element for a differential equation or drawing qualitative face portraits. And there you use the universal design UDL for learning principles, like of course the linear element doesn't have to be exactly on the right spot, but if it's nearby enough, then it is also fine. And you limit the space of inquiry by making your own menu items. These are not the normal GeoGebra menus, but the more dedicated ones for exploring the differential equations. So I think now I get to the last or the pre-final. Well, it was, yes, we're at least in the final stages. Students, but also the lecturers, were actually quite pleased with how it went. We had positive ratings in the evaluations. Actually, in Corona time, it went up. Mainly because we had digital material, so for us the change was not too drastic. They have mixed feelings about doing inquiry, because many still ask, well, what are the expected outcomes? Tell me what I should do. This is service education, that's where they expect that, okay, maybe you just tell me what mathematics is used and methods and techniques, and that's all. But there was a problem, and we are still struggling with it, with the programming part, the R task. As lectures, we saw it as opportunities for students to explore mathematics. And for students, they were too much busy with coming to grips with the tools, with the software. And in terms of instrumentation theory, you would say, well, they were not far enough in the process of instrumental genesis. It has to do with the fact that we misjudged how much the students would have learned already in the statistics part. But in the next slide, it says it was also part of double instrumental genesis of the lectures. When we started the course, or we started the design of the course, we personally had no experience with using R or RStudio, and also no experience in using these tools in teaching. And of course, we knew about several instrumental orchestrations that could help, like whole class technical demonstration, discuss the screen, explain. We did this, and it certainly helped students to familiarize with the technology. But yeah, still not, well, we have to still a way to go there. And that has to do also with the cultural change that the students need to make, and also in this program of learning to program. I think that there are still the traditional approaches that are dominant there. So you have to also fight a bit against that. And then I think, I'm sure now it's the practical issues, the final slide. Yeah, because I wanted to end at least in a positive way. Students, student teachers. I told you that we used student teachers in the design of the course, not only in delivering the course. And these were students, biomedical students, who had taken the first version of the course or the second one. And they actually got the time and student assistantships for redesigning the instruction of R and RStudio to make it more study friendly, accessible, let's say the wording, also the steps that you make in learning to use an environment like RStudio. So that was a big success, and I think that is one of the lessons learned for about the communities of inquiry. Although we were used in mathematics institutes to use students as experts in the teaching as well, but here it was really built into the design of the course, and I think that was beneficial for the student teachers. They learned a lot about education and things that they would not have expected behind designing a course, but also for the lecturers actually. So this last slide was thank you for listening, and hopefully it raises your interest in reading the Platinum book.
Thank you very much, André. Very interesting and a lot of practical guidelines, but also theoretical multi-level vision at the beginning. We have already a question from Dirk. Maybe you can speak it aloud, and then if you have further questions, you're very welcome.
Okay. André, thank you for your lecture. I was wondering, during the lecture, if you have inserted such an inquiry-based section, thereafter, do you need some special pedagogical strategy to proceed this lecture, or does it just go on, or do you adapt to it? What is there?
Yes, well, I told you it is a task where you can think about it beforehand. What kind of solutions would or methods I think the students would come up with, and how will I react to that? In the pedagogy, it's also what are you going to do in this 25 minutes as a lecture? Are you? It's clear that you have, after giving the task to the students, you have to give them time to work on it. So you have to be patient. So the first 10 minutes, I'm not saying much or hardly anything more if something is unclear. But I let the students really in small group. I tell them it's best that you talk to your neighbors, and I walk around a bit in the lecture room. In the corridors mainly, because it's in the real lecture room, but I can see what's going on. And also by walking around, I told you that 25% is disengaging quickly. Now that had to do with, for example, in this 8 hour in the whole day that they had full with lectures and tutorials. Some of them were, I think, just looking, is the train still going on schedule? So that kind of things. But by walking around, of course, if you start walking around, that means that students also are, well, I'm not stay using my smartphone. Yeah? So being in the neighborhood also stimulates a bit of, okay, let's go and do this task now. And it is the pedagogy is also with how do you react to the responses, so that you have to refrain from, a student comes up with one, let's say, it's an easy result that they can give back. I found an answer 1.05. And then you ask, how did you do that? But then you have to refrain as a teacher from taking over and saying, oh, yes, this is fits very well with this and this, and you continue. It's in order to stimulate. So it worked quite well, actually, during the lecture, that they came up with various solutions. They also, in the beginning, sometimes had to struggle a bit with what is actually expected from me. So that's why you walk around a bit and explain this a bit when they struggle with it. And at the end, I mostly give a view of, okay, there are still many more ways of doing it. So that they don't think that it's only what you can come up with, but this is a problem which is came into the heads of many people before already. Also, and then I think what is mostly effective in this process of this task is that they know also up front that they're going to implement their own invented method as well in the programming language, so that they can explore it more deeply and compare it also with other methods.
And there I had another question.
Yeah.
Because and that has to do with this R programming, for instance, or GeoGebra. It seems that students, they are if they are well versed in doing this type of thing, they can also make better examples, experiment, and so on. And so what do you think, and that is a very broad question and maybe hard and not so good to answer, but what's the relation between computational thinking, which is, and this inquiry-based interventions?
Yeah, well, I notice in my classrooms, besides these lessons, that students are more using GeoGebra. So it's just for checking things or making quickly a plot of something. So they are more used to using this kind of tools. But our studio is a bit different, because this is where you really have to program yourself. It's not like an easy tool. You have to explicitly program all the tasks. And that's where we have this difficulty, that the students, which we expected that they had already learned much more about programming in the first 2 months, that didn't work as well. And so we are working on improving that. But also, it turns out that the students are not so much used to that kind of environments anymore. If you are just used to a phone where everything is an easy app that you can use, and that all of a sudden you have to do all the details also yourself, then that is becoming more problematic. But once they master that, so if they overcome this hurdle of I have to program it myself, then it's more flexible. So then they can do more things initiated by themselves. Because at the beginning, they don't know what I see on my screen. Is this a mistake in my program? Or is this what's happening in the mathematics part? And you want them to be fluent, but also very self-confident in, okay, I can do this in this programming language. And yeah, well, we were maybe too ambitious at the beginning for that purpose. And what I've learned actually as myself as a lecturer, if it's about this instrumental genesis for the lecture, is that the problem in R Studio and R in general is that there are many, it's a public domain software, and there are many ways of doing things. And so if you go and search on internet, how do I do this? You get many different ways that have their own peculiarities. And what I've tried, or we have tried to do in our introduction to R, is to, let's say, okay, you can do it in many ways, but here you have a uniform way of doing it. This is the way how we specify differential equations. And then you can use this package, and that helps you in exploring. And well, if you want to go another route, then it's your own choice, but that is more difficult to support for us.
Thank you, André and Michiel.
Yeah, thank you, André, for this nice talk, a nice way of exploring the struggle in higher education to try to implement this way of working, because I can imagine it's a different culture for the students. I was wondering, do you also know the work of Berta Bacchiero or Marianne Bosch? They work also on differential equations, and then a bit more, I think, in this IBL way with these study research paths, where the students are really challenged to pursue their own questions related to population dynamics and try to discover elements.
No, we have not gone that route, so to speak. That has to do with the short time as well. It's 8 weeks.
Okay.
And we really want them to get into the Well, in some sense, we pave the way. We have a vision of, okay, we have numerical derivatives that has to be done because we are using that later. When they collect, when they have data involved. And we want them to go beyond what they read already in their textbooks. So, for example, we do enzyme kinetic studies. And if you look at most of the textbooks, well, then it says, well, forgive me the technicalities, but it says a Lineweaver-Burke plot. That's a linearization method. And yeah, that's there are many more and even better ones, methods for doing that, different linearizations. So we want the students to explore, to see that there is more than one route, not only the one that you invent yourself, maybe, but also in the literature. And this mimics a bit more. This mimics a bit more what you would do as a researcher. You would also first say, well, let's look what others have done.
But that's also part of their philosophy, that you can use books. But it's not only visiting books. It's doing inquiring the world and using what's there. And
yes, but I think here our 8 weeks. Well, although we have a lot of contact time, but for the let's say the study credits, we use them the whole 28 hours for one study credit. So, but then even then, it's a choice, because you could say, well, do less content and go more into the inquiry, invest more in the personal inquiry. But we wanted to give students a perspective on what systems biology is, what if they go in that track, what kind of mathematics they will encounter.
Thank you. And if I may, one other question, related to, I agree that it's difficult to say what is inquiry-based learning. It's a rather container concept, but at least what works for me is try to connect it to this inquiry cycle where you have these phases, and students do not really need to go through all these phases themselves, but it helps you to think how to balance activities. And so what I see here is mainly tasks that you give to students, but do you also give situations and ask them to question what mathematical question could you ask here, or what kind of hypothesis do you have? A bit related to noticing, but more explicit. So try to see all these phases that are relevant and try to involve them, engage them. Not always in each, but at least a more balanced choice than only giving tasks.
Yes, well, we have given more like this learning trajectory where it consists of tasks and explanations, and where students we focus on the reasoning and give argumentations for your answers, and not in and also in raising your own questions a bit, or raising your own trying out your own methods, but on a limited scale. You could say in these inquiry cycles, we always choose where we jump into the cycle, and we jump in at several positions, but not so much in the, let's say, the real world. And how do you model this? What kind of model would you use? And I'm thinking of other partners in Agder. They have, well, I think we were also a bit hesitating. In Agder, they have done more what you suggest, like coming up with your own models, for example. They have a more project on modeling, which is connected with inquiry-based learning. But then that turns out to be risky. In a university setting, because the students started to complain and went to the head of the department, and then they had to finish this course.
But it's not necessary that they have to follow all. No. When you ask them to pose questions, mathematical questions, then you can have a short discussion of 5 or 10 minutes, and then continue with your question. But at least then they have thought about it.
Yes, so well, in this enzyme kinetics. In the enzyme kinetics example, we ask for try to figure out your own linearization, because when you see that there are more ways of doing it, then you can be more adventurous and say, well, there are other ways still to do it. Maybe not very smart ones, but and also for other models. That's what we have done. But then it is more on a kind of side track.
Thank you, Michiel, for uncovering this kind of fundamental dichotomies, I would say, between content and personal inquiry, and between the demands of institution and the personal interest. Peter also had a question. Would you like to ask it, Peter?
Yeah, thank you. Thank you very much. I thought it very interesting. I have two questions. In what way does this relate to all kind of trials to include mathematical thinking in secondary school? And what's different here and what's more or less the same? And well, we don't call it inquiry based. We talk about mathematical thinking. So why did you choose the other name? And the second question is about how were biomedical teachers involved in the process, or is it just mathematics supporting biomedical studies?
Let me start answering the second question, because that's the easiest one. Because although the mathematics, basic mathematics course, I said this was a brand new course, it's not the first mathematics that they get from me in the years that I work on designing courses for life sciences. Before, the mathematics elements were embedded in larger courses. So it started off with from molecule to cell, and then you think, well, what has this to do with mathematics? But there, mathematics was part of it, and there the biomedical scientists were involved, because I was discussing with them what kind of things should be included, what should be the focus on. And so we there is a history of, okay, we already had courses with biomedical scientists collaborating. It is, we had scientists involved in our COI, but not for this course. But for example, a related course which also contains a lot about differential equations is a third-year course on analysis of neural signals, and that was together with the lecturer and the researcher in the neurosciences that was coordinating this course. So when we have a chance of doing that, we do it. But you know, also teachers, but also university people, they have a heavy workload, so they must be very motivated to work for a course that they are not personally involved in as a lecturer. And then the first question was more about, well, this is in secondary school, we are now focusing more on, let's say, mathematical thinking, and we don't, we stay a bit away from inquiry-based learning as a term. The easy answer is, of course, well, we promised inquiry-based approaches in our project, and then even if you are thinking along the project, well, maybe it's you could question, is what we have created, is this inquiry-based? Yeah, in what form? I think I could have called it mathematical thinking as well, but then thinking in the context of the discipline that they are aiming at. Mm-hmm. And there are certainly differences. At a university and the Faculty of Science, I think much of the education is directed towards, oh, you're going to do research. You have to have a master research project, have a bachelor. So research, or if you say, well, that's a kind of inquiry, that is something that is a shared goal that you would have students leading to become inquirers. It is it is easier in the sense that at least these students have chosen for a study in biomedical sciences or whatever it is, becoming a mathematics teacher if it's in teacher education. So there's still the question of why would I learn this? Why would I do this? How does this help me for my future? But it's different from in a secondary school level where you are broad, aiming for a very broad and diverse group. You don't know what they're going to do afterwards, even if they are, let's say, nature and technology profile that could be just the choice of a certain profile without thinking, oh, but I'm going to continue in science or engineering. Could still be something else. What I dislike about the use of inquiry is that in inquiry, I think for most of us at universities, the key element is there the intrinsic motivation. You are yourself interested in a certain problem, a certain topic, and you don't do that on demand. But here it's in teaching, so you have, let's say, from 3 to 5, we have a lecture, and if we have inquiry elements in it, then all of a sudden you have to do inquiry on demand. So that makes it a bit, yeah, well, you're not always in the mood for an inquiry activity, maybe also not in the mood for a mathematical thinking activity, but for inquiry, I think it is even a bit more difficult.
Okay.
But the focus is more on the conceptual. For most of our partners was on the conceptual understanding. In that sense, you could say, well, that's closer to mathematical thinking than the methods and techniques that you also have to practice. But you're better off with focusing on what is behind, what is underpinning these methods and techniques, because then you can use what you've learned there to try to understand other methods and techniques. And more independent.
Thank you. Thank you very much, André. Thank you for bringing more important topics into this discussion of intrinsic and extrinsic motivation. And thank you for the presentation. A lot, many things to think about further. We're finishing our today's session with that. I am inviting all of you for our closing of the seminar of the season of this year next time in June. André, you're also welcome. That will be a face-to-face session ending by a dinner in Utrecht. With Paul Dravers, who will be talking as a presenter. So more information is coming through the emails, and looking forward to see you live.
Okay.
Thank you once again.
Yes.
Thank you very much.
Okay.
Yeah.
Bye-bye.
Bye-bye.
Bye.
Oh, I said closing, but I saw